So, then welcome to, this is the session number 8 in the introduction to lattice Boltzmann, and I'm not calling this a lecture today because, well, we don't have a lecture today, but a kind of a coding demo, which always is a kind of a challenge, especially for me. Now you can see whether we are messing up. I'm not sure how long we'll take today. Yeah, my idea is because most of the people I already recognize have not hard time constraints afterwards. I mean, if you have, then just leave and maybe you watch the recording later. So, idea today is to take everything that we learned so far and try to cast this into some code. I've done this several times using Mathematica today, so that this leads to a very, very slow code. I mean, for one thing, it's in Mathematica, yeah, which is an interpreted language, a very slow interpreted language by that, and the other thing is we are not writing efficient code today. Yeah, very especially not, what we are doing today is not an efficient way of writing lattice Boltzmann method, because if you want to write an efficient code, you have to think harder. Yeah, I'm not trying to do it completely inefficient, but not really the way we usually do it. Just to get to see how, in principle, things work out, and we are going to do this in C++ in order to get a little bit more speed. And the reason why I've not done this in previous years was that when we do it in C++, it's difficult to visualize things. So what we are going to do today is we are using some Python bindings. Yeah, we bind our lattice Boltzmann kernel to Python in order to use the infrastructure of Python to get some plotting tools. Yeah? So this unfortunately includes some infrastructure that we also have to build. I will skip over this pretty quickly. Maybe all of you know more Python than me. I'm not a Python programmer at all, but with some help here from our students, yeah, we got this prepared in a way that I believe we can handle. Okay, so it means I have to do some inclusion here, binding, some NumPy, and we'll use vector. And we'll do basically the simple thing that everybody seems to start with, a lid-driven cavity simulation in 2 dimensions with a D2Q9 lattice Boltzmann method, and we'll use these population names as given here. I try to draw this stencil, which is, yeah, not very, okay, doesn't look very nice, I guess. So I called this thing LBM demo.cpp, and this, I guess, is the way I will call the class that we are using. So we'll write a class. Okay, I'll write this small LBM demo. So this is now the name of our class, and now we want to implement this class. So we have private attributes of the class, and with this I would say we work on a matrix code. Yeah, so say this will be a matrix code, meaning that we define a Cartesian grid inside a matrix. Yeah, so not with indirect addressing or some fancy things, but just a matrix. And this matrix will be defined by a number of rows and a number of columns. Yeah. By the way, I mean, usually in other classes where we have set up the same infrastructure, students would usually, you know, type this in parallel and implement it while I'm doing it. I understand now that this is not possible because we have different infrastructures, and I guess the people online have not been prepared for this. Yeah, but please, we really go through it line by line, and even if you're not typing with me, see this as a challenge in peer programming. So you're welcome to interrupt me and say, so this should be done in a different way. Yeah. I have a little bit of script, and I try to stick to the script. Otherwise, we'll run out of time. Yeah. But if you see that I'm making a mistake, just you know, step in. Okay. So definitely we have the numbers of rows and the number of columns that we will need. And because we are going to deal with a lid-driven cavity flow, so lid-driven cavity, not COVID. So I guess this is something that will look like this. We have a velocity, say, UBC up there, yeah. Then we have some boundary condition, and then some, I don't know, some nodes in between here, some boundary condition, yeah. Say, okay, maybe I should just copy this line a few times so that we get a picture. Oops, that didn't work. That we get a picture of how this would look like. Oops. And say we'll close this down here, right? So we have a velocity boundary condition on the top, then we'll have, maybe I do it like this. Then we have walls up and down, yeah. Maybe it's not very beautiful. I will do this in a different way. Say underscore is better, right? So, right? So, okay, then in between we'll have our simulation domain. Okay, so this is what we want to do. Maybe it's not the best place where I want to point this, but let's say we have we need this UBC as the velocity on the boundary, and then we need at least one parameter for our fluid. Can somebody give me this parameter that we would need in order to describe?
The velocity?
No, we've just given the velocity.
The viscosity?
Viscosity, right. So in principle, the viscosity, we could use the viscosity. Now I make my life simple and say we use directly the relaxation frequency omega. Yeah, and it's your problem how to calculate this. Yeah, okay, we can do this later here. So now what we need, maybe I'll take this thing out here and plug this here. Let's see whether so we'll have this D3 D2 Q9, right? So D2 Q9 with this population. So we somehow have to specify these populations. Now, there are different approaches how we can do this, and I'm always confusing the names. Yeah, so you could have an array for each of the population, for each of the points, and this would be called a structure of arrays. You could also have an array of all the points, and in this array of all the points you will have all the populations. This is an array of structure approach. So this is two possibilities that we could follow, and I'll just say now, please do it in another way yourself, but we'll now use a structure of arrays approach. Yeah, I'm not saying that this is a good choice or a bad choice. Yeah, so we'll just do it one way or the other. So structure of arrays means for each. So we are in the class. So the structure is already the class, right? So now inside this class we have arrays for each population that we need, and these are given in a two-dimensional framework. So, okay, we use a vector. We've included vector up there, so we are going to use a vector, which I'm going to use standard the vector template of C++. So my hope is that everybody is kind of a little bit familiar with C++. So it's two-dimensional, so we have to do a vector of a vector. Yeah? And because this is a template in C++, we have to specify that this is a template of floats. So now we have to do this for each of our populations. Say F, so as we specified them. Okay, so we could, because I just have them in front of me, I will just write them top line downwards. Yeah, so I'm going to copy this, make my life simpler. So then the next is F0P. So this is how we're going to name them, FPP. Then the next line is M0, no, nothing M, 00, P0. Okay, you see with the tooltip that I've already prepared these things so that they always give me names that already existed. No, I don't want to write this. I want to P0. So now you come to the last line, M0M. So please, everybody, always watching out for my mistakes, yeah, because I predict that it will not run on the first attempt. So, okay, these are our populations. Okay, so now in lattice Boltzmann we often said that we have to distinguish between the pre-collision and the post-collision state, right? There are ways to override directly the pre-collision state with the post-collision state, but they are a little bit complicated and we don't want to go in this detail today. Yeah, so I said this is not the most efficient way of implementing lattice Boltzmann code, but it is supposed to be a relatively simple way. So now if we say as usual that the pre-collision state is just the F, and we use as post-collision state, the F with an asterisk or with a star, I suggest that we just take the entire thing here, copy it, and also introduce the thing with an S. Now, unfortunately, I have not installed the proper tools here on this laptop, so I have to do this by hand. Otherwise, I would just mark everything and write S once. But okay, that doesn't work here. It's not so difficult, I guess. So now, what this is called is the so-called AB. Okay, I am probably writing this up here. Structure of arrays. So with so-called AB pattern, yeah, where the first is the A arrays, and the second are the B arrays. So A arrays, say this is pre-collision populations. And down here we do the B arrays, and this is the post-collision populations. Okay. Now we do, okay, so now we have this data. There's something important missing. Is anybody missing something? As variables, field variables.
The density.
Yeah, so in order to do some post-processing, we would like also to see the velocity, I mean, the primitive variables, right? So actually, they are mostly for post-processing, right? So they are also fields, so I'll just use this again and say there would be a field for the density, and there would be a field for, say, UX, and the field for UY, right? Okay. So this is, I think this is all we need in terms of variables. So what we have is, we have the boundary velocity, we have omega, we have the A pattern distribution, the B pattern distribution, and we have the macroscopic quantities. Okay, so now comes something, so we want to be able to transfer this data, which is now in the C++ matrix, we want to transfer this to Python. And in order to be able to do this, we have to do a little bit of infrastructures using a pi-bind array. So this I will just type now. I hope not messing it up. To be honest, I have prepared this I don't prepare this. I just asked ChatGPT to get me a transfer of a vectors in C++ for pi binding, yeah, for Python. So this is what ChatGPT came up with. So I'm just repeating it here. Let's see whether we can understand it. So there's a vector to num. So we make a function pi-bind of type pi-bind array float to vector to numpy. It's annoying that it already knows what I want to write. So this gets const std, this gets a vector, of course, vector std, and when I try not to make a mistake here, this will be very difficult. I should just copy it, but okay, now I've taken it upon me to write it. Okay, let's see. So there is what is this called? Dereferentiation. Yeah. So okay, so we get a vector in. And then what we do is, okay, it's not, I see that this was not written by me. I'm a very old-fashioned guy. It's 20 years ago that I learned C++, and in between, I've not done it a lot. Pi-bind, so this is new pi-bind 11 that we are using, array T of type float gives an array with the number of rows and calls. So this is not that. So this are, of course, attributes of our class. What am I doing? So, and then auto. So this is automatic. This is not how I would write C++. Sorry, but I'm now following ChatGPT. Auto array. So auto buff, of course, means that it's determining its type automatically, right? So we do auto array request, and then we do float pointer ptr is a static cast. Float pointer brackets, so buff dot pointer, and then we do the loop we do two loop for int I equals to 0, I is smaller than rows, plus I, first loop, and the second loop for int j equals to 0, j smaller calls, plus j, plus j, right? So next, open, and then pointer e times calls plus j is equal to. Now I have, I've noticed one thing. I noticed that Python and C++ order their matrix in a different way. So what is the first index and the second index is different. So they are exchanging X and Y somehow. I'm not sure why, but this is what I observed. And the solution to this is, even though I would usually write vector ij, I change this direction, yeah, between X and Y by writing vector ji. Yeah? So this is kind of the transpose of the matrix, if you will. Yeah? So, okay, we'll close most of these brackets. So we go behind this, and then we do the return of the array. Okay, so this is, I just hope that I didn't mess it up. And I don't know whether you followed it. It's not important. This is just the infrastructure for getting the C++ vector stuff into Python NumPy arrays. Okay, just infrastructure. I hope it will work. So now, as they say, now you can wake up again. So because this was not important, but now we'll go back to lattice Boltzmann and implement our public functions. So first of all, of course, we have to think about the pre-processing. Yeah, so we have to initialize our arrays. And this, of course, we do with a constructor. So we called our class, I always have to remind me, we called our class LBM demo. So our constructor here will be LBM demo. And we have to decide what we get. So obviously, we want to have the number of columns, which now I just call C, and we'll have to know our number of rows. Yeah? So then we also want to know our boundary velocity, which I'll just call U, and we also want to know our omega, which I call O. So now we basically set these attributes here as rows. Why do I start with rows? Calls. No, not this. We set this to C. Yeah, we set our rows to R. We set our UBC to U, and we set our, what is it, omega. Set our omega to O. Okay. So far, so good. Then we also have to initialize our vectors. Yeah. So, for example, I'll now go to write this in a new line because this will look ugly otherwise. We have UX, and UX is supposed to be a matrix that has the dimension C, and then inside this, so it's the vector of floats, and so it has dimension c and it has dimension r, and we want to initialize this with a value, and the value for velocity that we initialize is, I suggest, 0. Okay? Then we do the same thing for uy. uy, and then we do something similar for rho. Okay. So usually we'll... Okay, other question. How would we initialize rho? First of all, does it matter how we initialize rho? So does everybody think that it matters that how we initialize rho? I mean, it depends on what we are going to do with it. So usually, in every time step, we will calculate u, ux, uy, and rho from the population. So I guess we'll override this initial condition, and then it does not matter. However, just to be accurate, is it a good idea to initialize rho with 0? Why not?
Because it's divided, because to get the velocity we need to divide.
Okay, so yes, we are in a, you will find lattice Boltzmann codes that are a little bit more advanced than what we have learned so far here, yeah, where we do not store rho but delta rho, yeah. There are reasons for doing this, but we'll not do this today. Today we'll do it pretty plain, and then the density has to be a value other than 0, because in order to compute velocity we divide by rho, and if rho would be 0, then we would divide by 0. So we are not going to do this. We should set rho to 0. However, what actually matters is how we initialize our populations. Now this is really important. Yeah? So this here will be overwritten, but how we initialize our populations will be important. Okay, let me see. Do I do this in any particular order? We have the population F00. F00, it has the same size, it is C. Actually, I could just, okay, I'm going to save a little bit of time in order by just copying this. So, questions for the specialists. If the density is 1, density is 1, velocity is 0, what would be the population, what would be the value for F00? 4 nines. Okay, you know. Does everybody just know this by heart? Okay, I'll make a suggestion. We need, so usually now we come to a point where we need to do some calculations, and for this I like computer algebra. So we also teach computer algebra, I think, in summer term. I don't know. It's usually not for this. It's for the civil engineers. Yeah, but feel free to join us in computer algebra anyway. Yeah, I don't know whether it's not on the curriculum. So this is. But anyway. In numerics, we usually use a lot of computer algebra in order to solve our problems. And today we also use this to get to these values. So the colleague already know by heart, because he's interested in lattice Boltzmann, what this should be, but say we don't know. And now, given potentially the case that you are not very familiar with Mathematica, yeah, not all of you, but anyway, we are going now to use this in order to determine what our values would be. So the way I'm going to do this is to start from moments, and I write a function for getting moments in A and B, so we need this underscore in Mathematica to determine that this is a parameter of the function. It's not very important. So the definition of moments, as you remember, is taking the sum of, okay, we'll take some, okay, the sum of the sum of the sum. So we take two sums, yeah, because we are in 2 dimensions, of the index I. Now I have to do an unfortunate trick here. I have to add I am going to explain what this is for. So this is a power. So we take I by the power of A, and we have added here AA. I'm going to explain in a minute what this is for. Then we take J again plus AA by the power of B, and then we multiply this with Fij. So, and then we sum this. So the sum over I goes from I is -1 to 1, and from and in J it's again from -1 to 1. So now I introduced this dummy AA here because otherwise we would have the case that if we call this with A equal to 0, yeah, and I would be 0, yeah, then we would come to the case that we have 0 by the power of 0. And this is something that computer algebra doesn't like. So it will give me an error here. So I can, I mean, maybe in future versions of Mathematica this won't work anymore, but so far I can trick Mathematica by adding something else, here AA, and then if it doesn't know that AA could also be 0, it takes AA to the power of 0 and determines that this is 1. Yeah, which actually is a mistake in the program, but I'm going to use this mistake. And I will, after it has done this, I will set AA, so I do the substitution AA equal to 0. Okay, let's compile this and say we have moment 0, 0. So we see, okay, we get all our populations, the sum over all of our populations. And if we get this one moment M10, we get this moment. So okay, why are we doing this? We are doing this because in the lecture we talked a lot about the moments, but what we want to have here now is the populations. Yeah. So what we are going to do is we are solving, not solve. We are solving for the moments for the populations, and this we do by building a list or a table of moment A, B being equal to moment, say, A, B. I hope I'm not completely making nonsense here. And we build we build this table over A, so A is going from 0 to 2, 0, 0 to 2, and B is going from 0 to 2 as well. So, because this is two-dimensional, this will give us a list in a list, which is not good for the solving function. So I have to flatten this in order to get one list. Okay, maybe I'll, if not everybody is familiar with Mathematica, I just briefly demonstrate this. So say I'll take this here out, put it here. So I get now a table of the moments, of the equations of the moments, but this is a table in a table. Yeah, if I flatten this, it will come to be, just one table, right? So now these are the equations that I want to solve for the populations F, and this I do here by asking the solve function to get it for the different populations. So I don't want to write all of them, so I again write flatten table F I, comma j, and this is I is going from -1 to 1, and j is going from -1 to 1, 2. So, and then let's see. Okay, we get, now it solves, now this is the solution, yeah, given the moments as a function of the populations. We solve them for the populations, so now we can write the populations in terms of moments. So let's call this, I'm annoyed that this is a list in a list, so I'll just take the first element of this and I just get a list. This is not very important. This is, say, I'll call these things here my FFs, yeah? And now I have stored them in FFs, and what I'm going to do now is to substitute in FFs, I'm going to substitute the moments. Right, I'm going to substitute the moments. So basically I would have to write all the moments. So say we start with M00, right? So we could do it in one go, but I suggest we'll now do it just for the initialization first, yeah, and then you have to accept that we have to do it again later. So given we initialize with velocity 0 and with density 1, what would be the moment 0, 0? The density. So, and then this would be 1, right? Okay, so what's the next moment? Say we have the moment 1, 0. What is this? Somebody out of the internet, what is M10?
If there's no velocity, it's going to be 0.
Okay, yes. It is the x velocity, it is actually the x momentum, yeah? But if it's 0, if the velocity is 0, then this is 0. Obviously the same thing with this guy will also be 0. I mean, there's a more efficient way to do this, but now we're doing it by hand. So let's do M20. What is this?
That's rho times the velocity in
Yeah, but velocity, yeah, we assume that velocity is now 0.
And then is 1 times cs, or the speed of sound, squared. which
Squared,
is 1.
yes, and the speed of sound squared, we are not doing this now in that detail. The speed of sound squared is 1/3, right? So, okay, then obviously this means the same thing for that guy. 1/3, and then we have, of course, more. I mean, this is a non-asymmetric moment. The asymmetric guys are obviously 0, and the third order guys are always asymmetric, so they will be 0 too. Now, come to the actual values later, but so what is missing? Yeah, you can count them. Okay, if you don't, Mathematica helps you what is missing, because I can just substitute it in the one that is left in here, yeah, is the one that you still have to replace.
0, 3, right?
Hmm?
0, 3, which is equal to.
So you mean what this moment is? So the moment that we are still left with is m22. Well, I mean you see it here.
Yes.
Yeah. So m22. So what is m22? How do we get this?
We can see it as m2 times m2.
Okay. Yes. So m20. You mean m20 times m02
Yes.
divided by rho. Yeah. Rho is 1. So then this here is 1/9, right? So now we get them. And as you said, it's 4/9. Yeah? So, okay, this is, okay, so we use technology in order to tell us this here is 4.0/9.0. Okay? So my suggestion is obviously all the diagonals are the same, so we could proceed. Let me see, what am I doing? No, we proceed in order not to get confused. We are doing the cardinal versions first. This has the advantage that I can use my cheat sheet in order to get the right, not confusing the order. Let's see, I copy this. So, okay, we'll do the cardinal guys first. So this is P0. Okay, what is cardinal? Cardinal is this one, 1/9, right? So it's just 1 here, and then we have to do all the permutations of these guys. Meaning we'll have 0p, we'll have the same value, of course. Then we have m0, and we have 0m. 0m. Okay, so these were the cardinal ones. Now we do the diagonal ones. Say this is pp. So let's see, the diagonal ones have 1/36. Yeah? So we'll have 1/36. And I'm going to copy this another 3 times. So say this is now mm and pm and mp. MP, right. Okay. So these are the initializations for all the pre-collision vectors. Now we also need the post-collision vector, right? So I'll just repeat this. I'll just repeat this, and we just do this for the post-collision, and because I have not installed the right tools, I have to do it by hand, but I guess this is not so much because there are just 9 of them. So, are we done? I guess we are done, and since we are done, we don't need a comma here. So one thing that we need for our constructor, now we've placed everything already in here, so the constructor has nothing else to do. So I just open the bracket, close the brackets. This has been the constructor. I guess we need a destructor. Okay, I'll get a default destructor. I'll be demo. Okay, I'll keep this empty for the while, for now. Okay. Good. So now we have the initialization. Now, what are we going to do next? We could either just jump in the simulation, or we do a little bit of infrastructure first, I guess. Yeah, let's do some infrastructure first. So we have some functions that they get number of rows. Yeah, we just return. Okay, I guess just go and run. We return rows and get number, get num calls. Return calls. I'm not sure that we need these, but let's check. Close, yeah, that's not good. Well, yeah, it's later it will matter because we have to build the interface, and then it will matter. So, okay, there's one important thing that we need for later, namely that we have to write out these arrays and pass them to Python. This is why we need this pybind 11 array, that array t. Okay, I don't know what I'm doing here. This is just what the internet said that you have to do. So we get the row matrix, and and this we return as return. So now we use the function that we've written, vector to numpy, and we hand here in row, and this will be returned, and then we do the same thing for the velocities. So say ux what am I doing? Ux, so it's giving the entire matrix, yeah, and uy. And this would mean we'll have to hand in here ux and uy. Okay, so now we have, I guess we have a lot of the infrastructure out of the way, and we can go on to our void run simulation that takes the number of steps that we want to run the simulation. Okay, any questions so far? Are you following? Okay, then yes, what is the simulation doing? We'll have to run our simulation. We want to run our simulation for a certain number of time steps. I call this, doesn't really matter. I call this t equal to 0, t smaller than steps, and say t plus plus. Okay. So this will be the main loop of the simulation. So in the main loop of the simulation, we have to process all the nodes. Lattice Boltzmann is, of course, such that all the nodes can always be done in parallel. So usually we use parallel programming to run Lattice Boltzmann. We also have, in summer, we also have a course on parallel programming. Today, we'll just do it the old-fashioned, simple way, just write two loops inside each other to loop over x and y. Yeah? And don't care, I mean, the easiest thing that you can do is, of course, to use a pragma OpenMP parallel on one of these loops, and then you will have it parallelized, but this is not what we are going to do today. Right, so we'll do it for the outer loop int y equal to 1. Okay. Yes. Let's just go up here and remind of something. Yeah. So looking at this picture here, we apply the lattice Boltzmann code inside. So we want to have this lid-driven cavity example. Yeah. So we'll apply our lattice Boltzmann code inside this domain, and this domain is surrounded by these boundary conditions. There will be nodes, lattice nodes, at the peripheral of our domain where we do not apply the usual lattice Boltzmann algorithm. This is why we do not start at 0, so 0, 0. Actually, okay, I have to, there is another small problem concerning, that I should say in the beginning, with Python and displaying results. So Python places wait, how is it done? I believe it's placing this up.
Yes, in Python it's up.
No, the 0 is up.
Yes.
Okay, yeah, so Python, yeah, so this I find very irritating, and we have to deal with this. Yeah, so Python will place the 0 point here. Yeah, so usually me thinking in mathematical terms, I would put the origin of my coordinate system here. So here we'll put our coordinate system is assumed to be here down here. However, this 0 point and the 0 row, this is not part of the domain because here we have boundary condition. So we start up here. Yeah. So this is why we do not start at 0, but we start at 1. And also on the other side, on the other side of the domain, we also have a boundary. This is why, what am I doing? Y, no, y is smaller than rows minus 1. And then we'll do y plus plus. Okay, so open brackets, and for int, so in x it's the same thing. So I've not taken any particular care of ordering here. X is smaller than cos minus 1 x plus plus. Right. So now we are inside our loop. Okay, now, as I said, we are not trying to be very clever and very efficient here. What I'm going to do while processing these nodes is, so what we always need to process the nodes is to compute the quantities from which we later compute the equilibrium function, and for this we need rho and u. Yeah? So you can do this locally and save this to the matrix only when you do post-processing, yeah? Because I don't want to be clever today and don't care about speed that much. I will just write my row, x and y. I will write the matrix, and I'm going to use this matrix. Okay, we'll have to, so we'll have to compute rho. This rho is basically the sum of all these guys, x and y. Okay, I'm doing just a little bit of optimization here. I mean, remembering, you could say it's moment 0, 0, right? So of course, we just write the sum, yeah? In the later lecture, I will tell you that just summing up things like this is not accurate, for reasons that I don't want to get into now too much. It is always better if you have built large sums to do this in a kind of pyramid way, yeah? So not accumulating data in one variable, yeah, but adding two variables together all the time and adding the sum of them together all the time, yeah? So this is what we are going to do. We are putting the sum of f00 to a sum of f, say p, okay, have I done it in any particular order? f0 p0 plus f m0. So please, guys, watch that I'm not making any nonsense. X and y. So always at the same position, x and y. So this sum, I'll get this sum together with this sum, 0. So, okay, I said that we should always use this in a fashion like, so always make pairs. So it's called pairwise summation or pyramid algorithm. Yeah, pairwise, we build pairs. And what I like to do is always to get the ones moving in the opposite directions. Yeah. So now we have 5 of what we need. We'll also have the ones that go in the, let me see, I should actually copy the entire thing. So we are running a little bit out of space. So, okay, let's say we have PP, and then it will be MM and MP and PM, okay? So then again we have a sum of a sum, and we put this into a sum of a sum and add this to the number that will be the largest of them. Okay.
I have a question.
Yes.
This pairwise summation makes it more safe, right? Or more accurate?
It makes it more accurate. So the reason it's see, if you in lattice Boltzmann you build a lot of sums, yeah, and if you always accumulate numbers, the last, so if you add a small number to a big number, yeah, then you will have a bigger round of error than when you add small numbers together. So this is, you always try, and this is also the reason why I use the opposite numbers, you'll always try to add numbers of similar size, because if they are of similar size, they have the minimum round of error. So you accumulate, you always do pairs of two together, and then you pair them together again, and then, you know, you end up, of course, with 9 this doesn't work. This is why we have one outstanding here, yeah? But the one that we take outstanding is the one that usually is the biggest. And that where everything comes onto it last. So, we also need the velocities, right? And I'll do the velocities in a similar fashion, starting from what we had done for the row. Now I'll see, okay, so UX, so how does this work with UX? So it does not contain the zero population. So the first index is X. So then it's P00, obviously, minus this guy. Then this here, because it has 0 in it, it will disappear. Okay, I'll leave the bracket as they are. PP will have a minus here, and this here is, okay, I'll have a minus in, yes, so we'll have a minus here. So, are you satisfied? Is this it? Yeah. So then we'll do this, the same thing for,
we could also divide it by row, right? It's 1.
okay, so no, it's not 1. It's not 1. You're right. You are right. See, yes. So okay, so we first, okay, good. Yeah, this was a mistake. Thank you for pointing it out. So we have to divide by, because this is not the momentum, it's the velocity. So we have to divide by rho, but we computed rho already, yeah? So we just write rho, x and y. Okay, thank you very much for pointing this out. So then we have y. This does not contain this guy, and it does not contain this guy either, but it contains this guy, with this being plus in y direction and this being minus in y direction. So plus and minus in y direction, and plus and minus in y direction, okay? And then again, we have to, let's see, is this, the brackets are correct, right? Yes. So that's, we have to divide by rho, x and y. At least I hope so. They have different lengths because there's a minus here. Okay, yeah, but I believe this is still correct. Okay, if you see any mistakes, please stop me. So now we have rho u and ux and uy. And what we are going to do now is doing a BGK collision operator. BGK collision operator. So now you can go to either Wikipedia and collect the equilibrium distribution, or we can use what we learned in the lecture and determine our own equilibrium distribution, which we are going to do. And we are going to use moment with moment matching equilibrium. So for this, I've not saved a single time. So for this, we have to go back to our Mathematica here, right? And we have, what did we do? Okay, so this was the case for everything being in equilibrium, right? Now let's say everything with zero. Now let's say we are no longer in this, and we have to specify the actual moments. And the actual moment would be that we have, okay, we called this, let me see that I'm not messing it up, ux, yeah? So this is ux times rho, yeah? This is ux times rho, and this here is uy times rho. Okay, so this is what we learned. So what did we learn about m20? We learned that, of course, there is this 1, 0, plus there's also ux squared times rho. Just notice I'm taking the work from you. Yeah, I should have asked this. Okay, I guess then this here becomes clear. This will be plus uy square times rho. Okay. Now, this guy we can actually compute from this guy, right? So in order to use the substitute in Mathematica repeatedly, yeah, I have to put 2 slashes, yeah? So then I can use this repeatedly. So this should be moment 0, 1 times moment 1, 0. So what else do I have to do?
Times 0, 1. No, there it is.
Yeah?
Divided by rho.
Divided by rho, right? Because we have to normalize. So here, this guy is moment 1, 0 times moment 0, 2 divided by rho. This guy is moment 2, 0 times moment 0, 1, and also divided by rho. And the last guy is moment 2, 0 times moment 0, 2 divided by rho.
And the first one, the 0, 0 should be also rho, right?
Yes, you are right. Thank you for helping me out, because otherwise it just wouldn't work later. Okay, so Mathematica is really fancy, right? So now we get, by the way, computer algebra, in case you don't know, computer algebra, an invention of Stephen Wolfram, yeah, was actually invented to get the asymptotic analysis for the first lattice Boltzmann code. Yeah, so this was more or less the first thing that was actually done with computer algebra. Yeah, so I guess they are not yet completely beautiful. What I'm going to do is use I'm going to tell it that it should simplify it. Okay, I'll take this as a little bit more beautiful. I hope you agree. Okay, so, right, I should call this here FFEQ. So now we have FFEQ. Okay, since I don't want to type these things again, what I'm going to do is I'm using C form of, say, what are we going to start with? Say we start with F0, 0, 0. Let me see. No. Of course, this didn't work. We have to substitute this with FFEQ. Like this. So, okay. Now, unfortunately, it will determine that there's something of power 2. So what I'm doing before this is unfortunately a little bit of stupid Mathematica stuff. I'm going to say that whatever I call whatever A is there with a power of 2, I want you to write this as hold form, so don't change it again back. A times A. Didn't work. Why didn't it work? Okay, I'll have to look into my notes. Of course. Now I know why it didn't work. We have to substitute this guy first. Yes, so we have to do this first and this later. Oh, now it works. So I'll turn this in C form so that I can just take the liberty to copy this and plug it in. Unfortunately, what is not possible is to use the brackets here, because it will write the brackets differently. But this is something that we can deal with in a minute. So I'll do now, what I'm now going to do is write float FEQ 0, 0, 0 is equal to what I just got. Okay. So now I have to do this for all of them. Say I start with 1. This is doing it so ugly again. So what did I do in order not to get it so ugly? Okay. We are ugly. Can't we have it in a little bit less ugly format? Okay, so we'll have to deal with ugly format. I think this here is, how do we get it less ugly? I thought, yeah, this is this one here. So okay, I'll take, why is it ugly? Did we make any mistake? Does it look, I mean, we have minus 118. I think it looks correct, right? It's displayed in an ugly format. But do you see a mistake?
No, it's just a format, I guess.
Okay, what I'm going to do, because I don't like this, is, oh no, I'm confusing myself. This is -1, yeah? So it's f float feq m0 equal to this guy. So what it's okay, I understand what I have to do. So I'll change it a little bit by hand. I'll divide this by 18. And yes, so let's do the opposite of this. You know, the opposite of this should be the same up to the sign here, right? So we'll do this for completeness, we'll try it out. Float feq, what is it now? P0. See, I hate it that it gets this. It's supposed to help me, and it gets in my way. Yeah. There's another thing that I need to do. Oops. So let us just see whether what I said is correct. The difference. Well, it's giving it in a different format, right? Is it still the same? I mean, there's a possibility that I miss.
Yes, it's the same with a minus, just that the UX above is to the right.
It's once to the right and it's once to the.
Yes.
And why is it doing it that ugly? Okay, I mean, I remind you this is a 3-hour lecture, so because we are running not, if it was a 2-hour lecture, we will obviously run over time, but it's a 3-hour lecture officially, and this year I'm actually doing it, sometimes. Okay, let's continue with minus 1 here. Okay, there's a little thing that I can do, is when I do this wider, then it's potentially, okay, at least I don't have this break in the line. I am kind of in the impression that when I tested this before, I got it in a nicer format. I'm not sure why this is. I said minus, right? MEQ 0M, right? So it has this minus here that it would also have it here, right? Okay, so this makes sense. This makes sense. Okay, we cannot just ask all the time that everything works really very, very nicely. Oops, what did I do? Yeah. Float FEQ 0 plus equal to this guy. Divided by 18. So now we get all of the cardinal guys. Now we'll go to the diagonal guys, starting from -1, -1. Much better. Only the thing that I don't understand is why it puts this bracket here, because this is not necessary, but okay. See, computer algebra is only human, right?
It's considering the.
Yeah, so maybe I don't know what's FEQ. What did I say? Minus, minus. So at least this doesn't look so ugly. Basically, we are expecting now, and if I put this here, that this is just changing a sign, just changing one sign in this. Float FEQ, what did I do? PM, right? Okay, so this is the time of the day where I should get where I would eat an apple to adjust my blood sugar. Let's do PP. Or should I do, okay, I'm doing PP. Float FEQ PP equal to that. So now I'm confused myself because what we still need is MP. MP, this was not a good order. MP is this. Let me see. I'm putting float FEQ MP equal to this. So you guys are responsible if there's any mistake in this, okay? I'll change the order of these things. Put this one here. Okay, so obviously what is missing is that we have no local incarnation of UX and rho. So what we are going to do is to use find and replace. So recently there's something wrong. We don't want to do this everywhere. We want to do this in the marked results. Now I'm sorry, this was too late. So we'll do it in the marked results. We replace rho by rho x and y. Do it. Should be 9, right? Then ux replaced by ux. Do it. And uy. Do it. Okay, now we have our equilibrium. How do I get rid of this? So now for all of them, we have to apply the collision. Yeah, and because we are doing BGK, we are doing the same thing for everywhere.
We also need it for the distributions, right? Or is it going to be local? No, it's local and then...
So they are local.
Okay, yes.
Yeah, they are just defined local. Now what we have to do is to compute the BGK collision. So let's do this. Let's start with F00S after collision. It's X and Y. So how does the BGK collision actually looks like? It takes F00 at the position X and at the position Y. Plus omega times. So this is the one thing that I always have to look up myself. X and U. So we are now using the equilibrium 0, 0. And of this we have to subtract F00 X and Y. So, is this the right thing? The way I check this all the time is saying that when omega is 0, we get the post-collision will be the pre-collision. So this is true. Yeah? If omega is equal to 1, then the post-collision will be the equilibrium. This is also true. Yeah? So usually when these two things are true, I'm relatively confident that I wrote it in the right way. Now these things has to be done obviously for all of them. So say following the same order as above, we'll have here M, we'll have here M. So we have it in, we have it in 3 places. We have it in 1, 2, 3, 4 places. To adjust it in 4 places. So this is often done in terms of a loop, yeah, but we have not put these things in an array, so we'll have no way of doing this in a loop, so we'll do the loop by hand here, because it's only 9 of them, yeah? So P, 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 P. So next one was M, 0M, M, M, M. Okay, you're always watching out that I'm not doing any mistake. So we'll, I'm keeping a little bit the A on the previous where we had. So the next one would be P, 0P, 0P. What did I do with 0? So this is already the last one of these, yes. Okay, 0, 0P, 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 0P. So have M0, P0, 0M. Okay, yes, I guess this. So, and then the one in the diagonal, where up there we started with MM. 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 MM and MM. And we followed by PP, 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 and PP. And then this was followed by PM. PM, 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 and PM. So there should be only one left, MP. MP, 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 and MP. Okay, now we've done all our collisions. So now we wrote so usually, okay, so we did the collision and we wrote them back to where they came from, yeah? So usually after this collision, we should do a streaming, which now we could do it in a new loop. So do you suggest that we do it in a new loop, or do you immediately see that we have a simpler way of doing this? What does the internet? Are you still here? We are a little bit over the usual time. Hope you are not getting hungry. I'm getting hungry. What can we do in order to avoid a loop for the next for the streaming? Ideas? Maybe they have gone to lunch. No.
We are not in lunch, but I have no idea.
You have no idea. Okay, so there is. Okay, then it's good that you are listening, right? Yes, we could do an additional loop, but what we can also do is to write to our neighbor. Yeah. So what we already did, we read everything at the position where we do the collision. What we could do is to collect data from our neighbor and write on our current position. This is not what we are doing, but what we can do is we can do a so-called push scheme. So push scheme would look like this. So F00 is not moving. This population is not moving, so it will stay in the same place. Yeah, but when we come to fm0, this here, so this is moving in negative x direction. So it's supposed to arrive there at its neighbor. So we write it to the neighbor, x minus 1, okay? This guy here is moving in positive direction, so it will move on in the x positive direction, yeah? Is now the idea getting clearer?
Yeah, definitely.
Okay, so then let's do this for all of them, yeah? So we'll have here, no, it's minus, meaning we have minus 1 here, then it's plus 1 here, then it's minus, and then it's plus here, oops, plus 1, it's plus, minus, and it's minus, plus. I mean, I hope you see that M is minus and P is plus, yeah? Okay, so this is only one way of doing it. The other way is that we could write x and y here, and everywhere up here, we could write it in the opposite direction. Yeah, so we could done it here using No, not here. Sorry, not here, but not here, but up here. Yeah. So here we could collect the populations from the neighbor, and this is what we then would call a pull scheme, because we are pulling data from neighbors. Now what we are doing is we pushing data to the neighbors. Yeah, so this is why this is called a push scheme. Okay, now we implemented it in a push scheme. I'm not claiming that this is the most efficient way of doing it. It's just this is one possibility. So then we have done all the internal nodes. Then what we still need to do is the boundaries. Yeah, and because we are doing this very simple lid-driven cavity example, we have only boundaries in the surroundings, no boundaries inside. Of course, for your homework, you have to think about getting boundaries inside. So let's let us briefly see. When this here is the so this is the X that okay, no, I'll do it in another way. I do it completely in another way because I'm not completely sure this is correct. I'm going outside of the loop. Now I'm only in the time step loop, okay? In this loop, we do a new loop. We do a new loop for the left and right, so which is in the y direction. So we do this y again. We do the y again. I just very briefly for int y equal to, we start again with 1, right? We start again with 1, u smaller than y is the rows. Rows minus 1, y plus plus. So, and what we are going to do is we are doing the boundary condition for the left and the right. So, the left and the right wall. So left wall is, there are 3 populations that come out the left wall. And we call this F, which are the ones that are coming out the left wall. So the left wall is in negative direction, so what is coming out is going in positive direction. Yes, FP, let's see, in what order do we do this? Doesn't matter. FP0. Yeah, FP0 after collision is important. Yeah, at the position. So again, we are doing a push. So we have to write to our neighbor. Yeah, 1 and 1 and y, right? 1 and y. And now we have to get, so we're doing a bounce back, yeah, because this is a non-moving wall. Back. Bounce back is a non-moving wall. So what we are using is the population that came in. This is the one that's going in the opposite direction. This is fm0. And it is at the position 0 and y. Now we have to make a choice. I talk about, yes?
The syntax, I guess it wouldn't work in that way, right?
Sorry, yes. I'm too much into Mathematica. Also, this doesn't belong here. Okay. We have to make a choice here. So when I talked about the bounce back, I said there are two kinds of bounce back. Yeah? Which kind of bounce back would this be?
Would be the full one,
The what? Say again.
the normal one.
The normal one. So what do you mean with normal? When is bounce
Yeah.
back normal?
I have to check my notes. is the one which is not interpolated.
Yes, it's not interpolated. That's right. Yes. So, okay, it's simple bounce back, but for simple bounce back, we had two different cases that we could do it. We had a delayed and a non-delayed. Is this delayed or non-delayed?
This is non-delayed.
No, this is, unfortunately, this is delayed.
Ah,
We,
much less better.
wait. No. You are, right, sorry. No, it is not, okay, if it is delayed, yeah, because the one from the current time step would have here an S, yeah? So this one would be non-delayed. Yeah, it would give in the same time instance back. If we write it this way, it will be delayed. Yeah? So give me a vote. Do we want to do it delayed or non-delayed?
Could you please repeat the differences in how to write it?
Okay, let's say this here. Okay, we just so this would be delayed because it is not using the same time step but the previous time step.
Okay.
So then this here would be non-delayed. So do we want to use delayed or non-delayed?
Which one was more stable, or
So what did I say? Check your notes.
In the previous lecture, you said that the delayed was more stable.
Okay, let's take then the delayed one. Okay.
yes, much more stable the delayed one.
Yes, I'm not sure that it's in this case much more, but it's say okay. I'm still claiming that it's more stable. I've seen simulations crash or not crash according on this to this. Right. So what? Oops. What am I doing? So we have to do PP. PP is here in positive direction, and it's using MM. So from here, and now we have still MM. No. Stop me. So in negative direction, -1. Okay, but this is MP. So, okay. Satisfied? So this is the left boundary. Let's do the right boundary. Right, bounce back. Obviously, fm0s. So from the one before the last one, right? So this should be rows. Sorry, no, it's columns. It's cols -2, the last before the last one. Why? is equal to, the one going opposite is fp0. Okay, not S because we are. So this comes from the last one. It's cos minus 1, and it is coming from y. Okay? Is this correct? You're nodding. Good. So then the same thing with P, meaning we go one up here, go one up here. Same thing with M, minus 1 pp. Still correct? Okay. So then do a loop over x for int x equals to 1. You're finding something? Oh, yes, you're right. This is not correct. This must be pm. Okay, thank you for watching. X is equal to 1. X is smaller than cos minus 1 and x plus plus. Okay. So what am I doing? Let's start with, okay. I have a little bit of a problem in as far as we said that the display of Python takes the upper layer as x equal to, as y equal to 0. Yeah? So that's a bit confusing. Say bottom for Python. Yeah, because this means that we have to do the bottom at the maximum of y, not the minimum of y. Okay, let's just ignore it and do it. It's not the end of the world. F0ps. So let's not have now the opportunity to get confused because of this. Say it's now the maximum of this, so it's rho minus 2 is equal to F0m x and rows minus 1, correct? So, and then this again here for minus. So when it's minus here. It's minus there. And doing the same thing for plus. Plus is plus here and plus there. Okay, so this is the bottom in Python. Now we do the top in Python. So this is then F0M. F0M is x, and this will give us 1, right? Is equal to F0P x and 0. X and 0. Okay. Again, this with m is minus 1 p, and p plus 1 m. What am I doing here? Oh my God. Too much into Mathematica. See, you should not let the professor is usually not programming himself. Don't ever do this. So, by the way, we wanted the top to move. How do we get the top to move? We have to add the velocity. And if you remember from your script, we have to add the velocity in the velocity in the direction of the channel 6 times. So because I'm getting a little bit tired, I don't care whether it's now going to the left or the right. I just do. Yeah, minus 6 times the weight, and the weight we have already determined in the beginning of the lecture of this population in the diagonal to be 1 over 36. Yeah, so then 6 times 1 over 36, so 6 by 36. So it is 1 over 6. I just type it this way, times UBC. Okay, so and in one direction we have to subtract it, and the other, because it's the other way around, we have to add it, and I just don't care whether it's going left and right. This is why I'll just put it somehow, and if you don't like it, you can turn it around later. BC. So now we have implemented our boundary conditions. No, we have not implemented our boundary conditions. We have something missing. The corners, yes. Yeah, because our loop only it starts from 1 and yes, and goes only to one before. So we'll have to do corners. So corners would be f. So in the corners we only need one population that is missing, right? We have fpmS at the position 1 and 1 is equal to fmm 0 and 0, and I will not set velocity at the corners. I just set all of them to plain bounce back. pmS, so pmS is 1. Right, rows minus 2 is equal to fmPS 0 rows minus 1, right? Okay, I'm using my cheat sheet a little bit here. fmPS would be cols minus 2. Yes, cols minus 2. And, oops, not that one. And that's 1 is equal to fpmO. Now this is not what I should do. I should not use once delayed and once not delayed. Yeah, so that's not good. So that should be cols minus 1 and 0. Cols minus 1 and 0, MP. Yes. And then there's only one left, that is fmmS. This is cols minus 2, rows minus 2 is equal to fpp cols minus 1 and rows minus 1. Okay, now today everybody is late for lunch. Something wrong.
Close.
If
100, that line at the beginning, close. Instead of being close, it should be close.
close,
In fmmS,
fmmS.
To the right, it's close instead of, or it's
Close, yes.
it doesn't matter, but it's close.
No, it will matter. Obviously, it will matter. Yeah. So, there's one thing we still have to do. Yeah. So we have. I mean, we wrote from pre-collision to post-collision and already moved it, but in the next time step we cannot use the same pre-collision and post-collision. So we have to change between pre-collision and post-collision, and we have to do this for all of them explicitly. Fortunately, there is a function swap, and for those of you, you're probably not completely familiar with C++. What this is doing is it is exchanging the pointer, so the reference, to the arrays. So this is what we call a function that is basically free of charge. So this has almost zero cost. Yeah. So you're not moving any data around if you swap arrays in C++, not arrays, vectors. So we swap f00s with swap f with f00, and this is a thing that we have to repeat for all the others. So say p m again p, don't make any mistakes, this is difficult to find, m. So now we have the cardinal directions. Now we go on to take the diagonal directions, mm. So pp, mp, and pm. Okay, got it, right? So these are 9. Okay, so save this. I'm going to try to compile this guy just to see whether we made any terrible mistakes. Oh, we made some mistakes. Rows was not declared in the scope. Did you mean row? Oh my God, did I declare this as a row instead of?
Yes.
So I told you it will not work in the first instance. Row, oh my God. Oh, and then I wrote row again. Line 145. 40. Oh!
Because for loop, right? But it's using the. Should it be no?
Did I do this again somewhere? warning, FMP. Okay. So sorry, but this is always part of doing this stuff. So where was the last? Okay, it's expecting the semicolon. So this is very, then we started up with something, error expected. Okay, I guess we'll have, so very sorry for this, but this is always part of doing these kind of sessions. Okay, is this here a problem? Can't I use this inside okay, I don't know. Did I actually save it? I don't know. Okay, I think this is, if in case this is a problem, I don't know, why should this be a problem? Wait, this will all stay in the recording, yeah? What on earth? So there's somewhere a semicolon missing.
At the end of the
Private.
class, isn't it?
100. Okay, so there has a problem with the brackets.
Don't we need the semicolon at the end, or at the end of the class?
Do we have a semicolon at the end of the class?
Line 174. Do we need it? Yes. Or to get
Do we need it? What is this? I don't think so. Okay. Wait, where am I? I'm in the wrong. Blah blah blah. Fine. Okay, yes. So there's supposed to be one there, but okay, yeah, you're right. There should be a semicolon there. But we are completely initialized. Warning. Course will be initialized after the recorder. So are these all warnings? Is there, but
Yes.
error?
That one was the one of the column, but I guess that we have only.
Wait, is there? Can I? You know, it's not reacting. I'm sorry that this is so slow. Actually wondering. So, okay, all of you guys specialists help me. In calls, warning, will be initialized after in calls, is it the problem that we do one before the other? Okay, what I'm going to suggest now is, if this remains to be a problem, we'll have a look at it later again, yeah, because it's only a warning. I haven't had this warning when I tested this before, but let's try to not, I mean, we have now 12 o'clock, we'll have to get to an end someday. Okay, somebody has already left us, I see. Let's get to our actual PyByte module that we also have to do. Module, so we call this LBM demo, and we need here something that's called M. So again, this is something I'm not very familiar with. I'm just using what the internet told me. So we'll do a PyBind 11 class LBM demo PyBind class LBM demo M, and we call this LBM demo. So in this we have to get these functions that we have to get the init function PyBind 11 init, so this is the constructor init. So our constructor takes an integer rows and columns, int float load, then we have def. Okay, we'll have we'll define the function for get num rows. That's okay. For dereference LBM demo, LBM demo, and get the function get num rows. So the same thing for the columns. Get num cols, get num cols. Get num cols. So, and now the important stuff is to actually get the matrix for row mat, get row mat, get row mat, get row mat, and the same thing for the velocities. So this would be get ux mat, uy mat, And then one thing that we must not forget is to get actually the run function, yeah? So otherwise we cannot call it. So all of this is to export things to Python. Here we need a semicolon. Consts. Init. Okay, so we'll have something wrong. Def pybind 11 init int float. Pybind class. So this definitely has to be small. So still it has a problem with the order of initialization. I don't know why this is a problem. Okay, here we have an error. Root, oh no, that was the previous compile, yes. Okay, warning, LBM calls will be initialized after int calls. Why is this a problem? Does anybody know why this is a problem? It compiled something. Okay, let's try. I know it's getting late. Let's try to use the stuff. Anyway, let's see whether we messed it completely up. So what we need to do is we have to import what was it? LBM demo as LBD, say, as LBM demo. Import matplotlib pyplot as matplot. Did I mistype this? Matplot.
Without the H in math.
It was, it's not, okay. As PLT. Oh, let's see whether this actually works. Hmm? This one, yeah. Okay, sorry. Yes, I was. Import no module name LBM demo. So this is the question ls.
Maybe it has to be with capital LBM.
Because it's okay, could be LBM. Okay, let's see. Okay, so that was it. Let us see how do I open a new space here. Code plus code. Yes. Okay, let's see whether we get an LBM LBD dot edu. No, sorry. LBM demo. Now we have the initialization, say we get it 100 times 100 times, so now we have to set the velocity. So this was the dimension, the velocity I set 0.1 and the viscosity I set 1.8, okay? Let's see what happens. Okay, something happens. Then see whether we can actually run this guy, lbm.run. I'll just run it for one time step just to see whether something happens. Okay, something happens. And okay, since now something happened, I want to display some data. I'm going to use, I think we'll need a few more things here. Import numpy as np, and this again is something I got from ChatGPT in order to, I asked it, so how do I display something continuously? So I use artificial intelligence for this, I'm sorry. Import clear output. So this is now. Just run this again, run this again, run this again. So it's not complaining. So let's try to get some output. For E in range, say 1000, yeah? Say we do a run for, I don't know, 100 time step each. We compute ux as lbm dot get ux mat. By the way, did this, I hope, did I do something wrong? Let me see whether this actually works. lbm get ux mat. Does this get? Okay, yes, so we get something, yeah? Okay, let's, right, so get these, uy, lbm dot get uy matrix. So we got these two, then what we do is we compute the square root of them, np squared, I mean the magnitude of them, this is ux. Now we have to do this in this way, times 2 plus, times 2y. So this gives us the magnitude, and now we use our plot, plt, im show we oh wait, I think we don't need this, sorry. We don't, okay, not again. If we do lpem show, okay, we do, then comes something, okay, I asked ChatGPT, don't remember what this, where it is. Is this, what is this meaning?
It's the color map. So
it's the color map, or maybe.
If I remember, that's green and yellow.
Okay, maybe we change this. We show a color bar. We are running out of space here, color bar. And we said plot title f times depth. Say I'm doing something that I should not do. We could say no. Not saying something, don't do this, we should, that steps is equal to 100 and put here steps. And
also there are two, after the 4, 2 dots,
there's a dot missing, and this is why it doesn't, there's a column.
LBM, or the name of the class, in the method run, it should have the class before.
In the run.
So the function is LBM run.
Also LBM, sorry. LBM, not the class, but the object name. Yes, sorry. So, and then this is I times steps, should be, right? So, and then plt dot show. Do you think this will work? No. No way on earth. Run all.
Or it would show the last one. Oh.
Okay, it's not increasing.
Oh, the first one then.
It's showing the first one, yeah, because interrupts. Because what I did forget to clear it. Yeah? So I have to clear. Wait, Okay, I see. I have to start with I guess I have to put a clear somewhere, but I can only put a clear somewhere when okay, I don't know. I put a clear here. So this clear output weight true. So this is what ChatGPT said. Restart, run all. Trace back, no, didn't work. Why didn't it work? Because I did this before. Okay, so I put this in the wrong place. X, I have to first compute V and then do it. So, okay. See, we'll never get this done without mistake. So, okay, something, okay, not too bad, not too bad. Okay, how long did it take? 2.5 hours, right? Sorry for taking longer time than expected, yeah, but at least it works. So, any questions to this? Some people have left us. Okay, I guess what I'm going to do is I'm stopping the recording. Yeah, thank you for attending. Stop.